my name is Halyna. I'm a senior data scientist in Delivery Hero, and what I'm doing for the last year and a few months is that I'm building like ML-powered search engine, and the topic that we'll be discussing today is actually this ML-powered search engine. We will discuss like a broad range of things related to like what are the challenges that usually ML engineers are solving when they're working in search teams, and how search engines they work in general, and also like what metrics do we usually evaluate, what are the challenges that we usually see, and we will try to get this like general picture of what are the things that we are usually observing when we are working in the search team. So this will not be like a very like detailed method-oriented speech about like some specific algorithm. This will rather be like a talk to give a broad understanding of what's happening inside search teams, how they're working, and also what are the challenges that we're usually observing. So yeah, most likely you already know how search engines work. So usually we have like these big 3 steps, which is crawling, indexing, and ranking. We will not be speaking in details about like crawling, and we will not be speaking in details about ranking. Like we will just be talking about ranking more on the level of the ML models that are doing ranking, and we will not be speaking about like how Elastic, for instance, can do ranking or something like that. But yeah, we will discuss some basic stuff related to it. So most likely, you know that like we can build a crawler that will be visiting different websites. It's like usually when we're talking about a crawler, you imagine some kind of a spider that tries to visit all of the links from a certain search page. And yet it tries to gain all of the information from the search page and from the search pages that are connected to the search page by some link. So yeah, like we will talk in some details about some very basic web crawler, obviously like advanced web crawlers that Google is using, or some other like DuckDuckGo, for instance, some other big search engines you are using. Like they are much more advanced, but we'll just talk about it like into like some simple stuff. So web crawler starts with a list of URLs to visit, like this is called the seed, and for each URL the crawler finds links in the HTML, filters those links based on some criteria, and we add these new links to the queue. And we'll also have a look at basic Python code. I want this talk to be more hands-on. So yeah, we'll have a look at the code, and all the HTML or some specific information is structured to be processed by a different pipeline. So here you can see some seed URLs list. We are adding these URLs to the queue. This is URL queue. We are like visiting these URLs, then we are removing visited URLs from the queue. And like when we have visited some URL, when we're visiting a URL, we are extracting URLs. We're extracting HTML information from that page. And this HTML, it is usually stored in some data storage. It depends obviously on the task that like we are resolving, what kind of storage should it be. So to build a simple web crawler in Python, we need at least one library to download the HTML. Usually it is Beautiful Soup, usually it is request library. There are things like Scrapey, and most likely, you know, some more advanced stuff, more modern things. So this approach is very basic, probably outdated. Yeah, so what you can see here is a basic crawler class, and in its constructor, you can see like visited URLs and a list of URLs to visit that we are going to we are going to update this data structure. So when we're downloading this some URL, we're just calling request get method, and when we are trying to get some linked URLs, we're using Beautiful Soup library. There are obviously a lot of alternatives. I'm personally not a big fan of Beautiful Soup, but it still works, and it's been working for many years. So yeah, we are just yielding different paths when we are like going through all of the links that have been found on the page, and we are looking for these links using find all method. So another method that is present in this class is that we are adding URLs to visit using this simple method. We are doing our crawling using iteration through linked URLs. So we are calling this get linked URLs method. It's implemented here. We are calling then this method in this loop. So we are like we are yielding each URL using this method, and in and each URL we have yielded, we are passing it as a parameter to this method. Hope I explained it well. Here we're just running this code while we have some URLs to visit, and just to like explain it even maybe simpler, you can have an output like of what it looks like when we call this code. So the code above, it defines a crawler class with helper methods to download URLs using this request library, and we are getting this linked URLs using beautiful soup library. So this is a very simple example, but sometimes it's also fun to play with. There are some disadvantages, obviously, of this simple web crawler, and most likely you can already assume that ideally we should use like async.io, ideally we should use more efficient libraries, ideally we should think about what kind of asynchronous patterns we should implement here. So this crawler is slow, it doesn't support parallelism. It takes about 1 second to crawl each URL, and each time we make a request, we wait for the request to be resolved. And like ideally with some async code, we should be able to do some other work while we are waiting for the request response. We don't have any retry mechanisms. The URL queue is not a real queue, and it's not a very efficient data structure. So yeah, ideally we should optimize this code, but yeah, so this is very basic. This is just an example. So here is a more advanced, a better example, a better diagram for some better approach that could be like implemented. So here we are having like a few spiders that are like scraping those URLs, and we have an engine that receives responses that receives some responses. We are having like several pipelines, and we are having also like a downloader like of these responses that are being sent into the engine. So yeah, like we will not discuss this diagram in more details. Like here is the link like to a more advanced example. I think they're using like Scrapy here, if I'm not mistaken, but like ideally we see that even a bit more advanced like approach, it requires already a more complex architecture that would require like distributed system architecture with like all of the requirements that we can put into distributed system, and it also requires more advanced data structures and asynchronous code. And we like described in this list that we have a scraper, that we have an indexer, and that we have a ranker. Like these are usually the most common parts of the search engine. So now let's talk about inverted index. Most likely you've also heard about it. It's very simple to build in Python. So it's a system where in a database of text elements where we have compiled the list of words like keywords that are contained within some documents. We're using tokenization to get these terms, these words from the documents, and we are using this tokenization to reduce the amount of words. So here is the example, like to explain it a bit better, I think, because this definition probably is not the best one. So we have this first document, the big sharks of Belgium during beer, and we see that doc ID, let's say that this is this document has ID 1, so it has frequency 1. So because like the word there appears only once in this document, in this first document, but on the other hand, like word Belgium, it appears in the first document once, and in the second document it also appears once. Word beer appears once in the first document, but it appears twice in the second document. We see it in each of the sentences of the second document. So this is here inverted index looks like that we want to tokenize our sentences, and we want to count the number of appearances of each word in each of the document. Number of appearances, I mean frequency. Inverted index, it is usually understood as a simple key value dictionary, and it is also usually implemented as a key value dictionary in real databases, where each term we store per each term we store a list of appearances of those terms in the documents and their frequency. So here we can have a look at the class appearance. So this is just like naive, very simple naive class. It just represents the appearance of a term in a given document, along with the frequency of appearances in the same one. So it just actually prints out stuff. It just represents a single appearance of a term in the document. Here is the simple implementation of a database. Actually, it's like very simple to some NoSQL database here, or maybe it can be even compared to Redis. So this database class is a fake in-memory DB used to persist the documents after they have been indexed. So like in memory, so this is then more similar to Redis, I think. So here we see that we can use get method, that we are like accessing this data structure. This is the main data structure that is in this attribute DB. So when we're trying to get an element from this DB, we are running self DB get, obviously. When we're trying to add an element into this database, we are running update. And when we're trying to remove something, we're calling DB pop from this dictionary. So this is just kind of wrap around Python dictionary, just to have some additional methods like wrapper, and just to have it in like more syntactical sugar way, let's say. And here is the implementation of inverted index itself. So we have the index, which is a dictionary, and we have a database, which is also a dictionary, as we've seen previously. Wrapper, it just prints out stuff, so it just prints out our index. So when we're trying to index a document, we are trying to process a given document and save it to a DB. So what we're doing by processing here, we are just doing some simple tokenization. Well, we are like cleaning text. So by cleaning, we are just removing some special characters here. Then we're splitting this text. And then we're trying to fill up our appearances dict, which actually calculates how many times each term appeared in each document. And after that, we are trying to update our index, our inverted index. And to do that, we are just like creating this temporary data structure to update our inverted index. It is update dict. And yeah, like then we're just updating our index using this update dict. And after that, when we have done that successfully, we are adding this document into our database. And when we are doing lookup, then we are running like, then we're trying to find each term from this in this query for like each word. So we are trying to split our query into words, and for each word in this query, we are trying to find it inside our index. And yes, so the result that we have is a dictionary where key is the term itself, that if it has been found in the dictionary, and the value is actually the value of number of, it is ID, and it is number of appearances. I think, if I'm not mistaken, here inside this data structure, if I haven't made a mistake anywhere. And here is our main function. This is database. This is our inverted index. So here we have two documents, let's say, like the same example that was previously shown. We are running our index document methods, and then we are trying to look up some terms. So let's say that we were looking like for Belgium. So Belgium appeared like once in this first document, and it also appeared once in the second document. So this is the expected result. So this is just a very, very simple implementation of things. Like this is the actually the core of search engine that we're trying to build this inverted index. Yeah, and like after discussing that, I think it makes sense to switch into some more advanced like tasks and like actually the tasks that ML engineers are trying to resolve, because what search engineers and software engineers are usually working on is that like usually Elastic is being used, like either Elastic or Apache Solr, they're being used in the majority of the companies. And what search engineers are doing is that they are maintaining this Elastic, they are like working on its configs, on its settings, they are like doing also sometimes some kind of like quality assurance, making sure that okay, like Elastic works under some load and that the Elastic works adequately for different kind of queries, and they are writing some APIs for this Elastic and so on and so forth. So this is usually the part that search engineers and software engineers are maintaining. Also maybe some ETL around this Elastic. And what ML engineers are doing, I've not made it as a separate slide because I think it makes sense maybe just to discuss it, is that we are trying to like implement all of the steps that are happening inside in a search engine in a smart way. So we are trying to, first of all, make this query that like goes into the system, make preprocess it if needed, to expand it if needed, to maybe classify it if needed, and also to autocomplete it if needed. And also what we're trying to do is that we're trying to do ranking of the results, and we'll talk about ranking a bit later. So there are actually different architectures of like how you can have your system, search system implemented, and this is just one of them. I don't even know like what is the current architecture inside my company, because like it's huge, like a lot of services, a lot of pop-up subs, like a lot of dependencies. So it's a very big microservice architecture. So here is just an example, and we'll have a look at several other examples. So a user is sending some query, we're doing some data preprocessing like stemming, text segmentation, lemmatization, removal of some special characters, whatever you can think about. And after that, we have our like collection of documents that we also have preprocessed. Usually we store them inside some database, and they have already passed that inverted index stage. And after that, we are trying like to find some documents that can be found inside that inverted index, and we are trying to rank them properly. But in many cases, the problem is that, first of all, we cannot find some documents inside our inverted index. So sometimes like these documents that we have found, they are not relevant. This can also be the case. So what should we do is that we should help our system to understand what we want it to, what results we want it to return. So to do so, like we can implement a lot of query understanding steps. Like I'm working in a query understanding team, and what we're doing is that we are like expanding these queries, classifying these queries, doing sometimes some named entity recognition, and like trying to get as many context out of these queries as possible. So query expansion is the process of reformulating a given query to improve retrieval performance in information retrieval operations, particularly in the context of query understanding. Query expansion involves evaluating users' output and expanding the search query to match additional documents. Also, in many cases, query expansion is used to reduce zero results rate. Most likely you've heard about it. So zero results rate, it happens when the document is not present in the inverted index. And what it means is that like we just don't have matches inside it. And for instance, for our case, let's say like user is searching for a burger, and let's say that we are not selling any burgers, like all of the vendors that are selling burgers, they are closed. But most likely if user is searching for burgers, maybe he or she is also interested in donors, or maybe French fries, or maybe some fast food, or maybe some ice cream, or maybe some, I don't know, wraps or something like that. And we can have vendors that are selling it right now. So then it is a case for query expansion. Query expansion involves techniques such as finding synonyms, finding semantically related words such as antonyms, meronyms, hyponyms, and all of the stuff from WordNet, and finding all of the various morphological forms of words by stemming each word in the search query. And also we can find spelling errors and also automatically search for corrected form by like expanding our search query with the proper correctly spelled version. And we also can rewrite the terms in the original query. Here is another like example of the architecture that could be present where query expansion is also present. So we have our documents database, and we have like this inverse indexing part here, like where we're doing text processing, clustering, terms waiting per cluster by terms waiting. I mean that we can, in our example, we just calculated frequency, but we can also calculate TF-IDF, let's say, or some other kind of metric, what we want. When user is entering the query, we can process its terms, we can do query expansion as shown here. And for instance, in this case, we have some user level, I think, like result retrieval, where we're loading users cluster preferences and using some supervised machine learning as described here, we are trying to return the results to the user that are relevant. So this is the case when we're also introducing some like metric of relevancy to the users. What can be our data processing steps for query expansion? This is very trivial: text segmentation, stop words removal, and stemming. All the stuff that we always are doing for other NLP challenges. What can be said about model training? Here I'm talking just about like a word-to-vec and about some approach that was introduced in one of the papers, but this is a very general thing for a lot of companies about how they are resolving this query expansion problem. Like in many cases, you just need some word embedding model, language model, and using this language model, you can actually expand your query. And in many cases, this is exactly what you need. So it can be fast text, it can be word-to-vec as is described here. It can also be BERT, it can also be XLNet, whatever you like, Almo maybe, like, so it depends on your latency, on your requirements, and on like what you want to build. Skipgram, obviously it's better in word-to-vec case because like we are trying to predict multiple words given one word in the skipgram setting. But yeah, actually you can select the model you like, because the idea here is like to expand the results using as many relevant queries as possible. Also, like in many cases, like we have like 5 or 10 queries limit, because like this is usually the settings that we need to also set up. Like this is the parameters that we need to set up in Elastic, that okay, like we should have like 5 expansions, let's say, for each query. And yeah, like this is usually how query expansion is being made. And so like when we're doing model inference, word vectors are used to find semantically related terms to this query. Yeah, we're using usually Euclidean distance if we're talking about word-to-vec, but remember, we are not only sticking to word-to-vec in any case. We can also use some nonlinear distance metric, for example, and we are running exhaustive search to find all possible candidate vendors. Expansion terms are either similar to the entire query or to its individual terms. And yeah, like before we go into WFST, like we will be talking also today about evaluation of these things. And the trickiest part here is that we always have a discovery problem if we would like to evaluate query expansion like directly. If we would like to measure, okay, is this term right? Is this term right? Like if I have like let's say like 5 words that are expansion of some search query, and this is always a challenge because like some of the data annotators, first of all, like they can have different opinions. Second of all, like we can have a bit more data, and it's always tricky like to somehow automatically label data, do some kind of weak labeling initiatives and algorithms. So this is always a challenge. So most likely, if you would like to relate your query expansion model, you will need to stick to ranking evaluation metrics, and we will talk about it a bit later. here also comes the question that is related to like both query expansion, and it's also related to query autocomplete, and we will be talking about autocomplete soon, is how we would like to store our results of the model. So when we're talking about query expansion, maybe a relevant answer would be just to have a model and just to return, inference from the model, which is the right answer to this question. But another answer to this question could be is that we can use weighted finite state transducer. I personally don't really like this full name, so it can be like shortened to WFST, and WFST is good at modeling H&M and solving state machine problems. And WFST, it is like usually used in the recognition of the voice problems, and it provides a natural representation for hidden Markov models which are used in the phonetic case. So for instance, here you can see that we would like to transduce phones bill into bill. Yeah, so the user is saying something and we're using this transducer to convert what where the letters that were spelled by someone into some real word. Also WFSTs can be used for context-dependent phones, pronunciation lexicons, and grammars. Pronunciation lexicon transducer below decodes phone sequences into words, as you see here. But we will talk a bit more about it. But most likely, if you are familiar with hidden Markov model, most likely you already have some ideas about what is WFST. So in WFST, weights can be associated with edges as costs or probabilities, and this is already like Markov chain. Most likely you recognize some intuition that is very, very similar to Markov chain here. And diagram below, it represents the world level grammar transducer in modeling a bigram language model. And here we have the calculation of the likelihood of the word sequence. And this key strand of this WFST is composing transducers together to build some structures. And we'll talk about what it means a bit later as well. Transducers also decode the mapping between the input and the output label sequences. So what we have here is that, for instance, we can start from state 0. And 0 here, it is an index where we begin from. And we when initially we start with state 0, we can say, okay, it is more likely that the user or someone will start with the word, let's say, Jim, and Jim and Bill, you see they have equal weights, equal. These are not probabilities because you see that they are not normalized, but equal weights. And let's say we started with Jim, and we can continue with the word road because this has the maximum weight here. So most likely, most likely sequence here is Jim road or Bill road. A bit less likely sequence here is the Jim flat or Bill flat. Obviously, if these are probabilities, you can always use this product rule of probabilities. You can multiply this probability by this probability, let's say. And finite state automation, this is another word term that is also used in WFSTs, but actually all of this terminology, it is very, very transferable to hidden Markov models, and you can call things from here, there are synonyms in hidden Markov models, so it's just the point of terminology. So finite state automation is a model defining a state machine with transitions between states in response to some output. So in the state S1, you see here S1, if an input C is received, it will transit to state S2. So it's just a diagram which tells us how can we proceed from some state to some other state dependent on the input that we receive. So input can be a letter, input can be a letter that we are some sound that we are producing in this recognition of voice context, and it can be basically anything. A finite state acceptor is a finite representation of a possibly infinite set of labels. So what it means is that we have cases accept reject here, and what it means is that we match in a sequence of labels to pass between the initial and the final state, and we can accept if we find such path, and if we can't find such path, we reject it. So for example, the input sequence ABCA will be accepted. So have a look, ABCA. So we can follow the arrows and we can go from initial state to final state by following these weights. And BCB will be rejected because we can't go from B to C, and yeah, we can't go like backwards here. So we can go from this 3, this node with number 3 into this node number 5. So this is what we can do. And also we can add weight to each arc, and this is a called weighted finished state acceptor, and this will be already very similar to WFST. So WFST is just a finished state transducer with weights. And a path around through this transducer maps the input label sequence to an output label sequence. So this is actually what it does. If an arc is empty input or output, it is usually empty result. And how it works in practice is that, first of all, it is useful for the case of language models. So because let's say that we start with word using. Here it's an example of language model. Yeah, this is the language model. So using, we can then go into data, and then using data and go to is, and then it is better. You see here, so this is like a data structure to represent language models, but it's not limited to language models. If we have conditional probabilities of transferring from one word to another word, like by transferring, I mean saying next word before previous word. Also here we are preserving a Markov assumption that each word depends only on the previous word, which is not true, but we are doing this simplification just for the sake of being able to represent the data in such a way. And here these weights, they can be also treated as actually prior probabilities. So this is the prior probabilities. Here, these are indexes actually that we are getting from here to here, but we could also have prior probabilities inside these nodes that this could be, for instance, prior probability of word using. Here it is data and so on. Its main purpose is to calculate the probability of a word sequence, the grammar. So here we're calling this sentence a grammar that can be constructed. For the second case, it is a pronunciation lexicon. So here we're trying to construct from some sounds, we are trying to construct words. So we are trying to construct a word duo, I think. And once an input sequence is accepted, the first arc output data, with the rest output empty labels. And this is an interesting stuff, but why we are talking about WFST? This is because WFST is the structure that is often used for query autocomplete, and we'll be talking about query autocomplete now. And what it means is that we are using prefix matching in many cases in query autocomplete. So maybe we can go to our website now. I wasn't preparing any kind of the demo, honestly, because I was a bit blocked by other tasks, but maybe we can go to Foodpanda Philippines. Let's say we can go to Foodpanda Philippines and we can have a look at maybe our autocomplete, but I will need to select don't allow some delivery location where they're delivering, because I'm not on Philippines, unfortunately. By the way, you can ask questions while I'm setting things up. So do we have autocomplete here deployed? Yeah, we have autocomplete here deployed. So this is our autocomplete on Foodpanda for Foodpanda Philippines. And see here, what we have is that we are using prefix matching, and what it means is that we are trying to get the input for this WFST as the first letters that we are entering. So we are entering KF. Yeah, and it can be continued using like all of these sequences of letters that could form a valid query. So I will not be talking about how we are actually forming these suggestions in this particular case, because I obviously can't do that. But the logic is that we're using prefix matching, because like we're typing Kiev, and using this prefix we're trying to complete this query. So we can also do, I don't know, McDonald's, let's say. It's pretty slow for me, I don't know why, maybe because I'm in Berlin. But yeah, also we can complete it like McDonald's or something like that. Also not very good suggestions, because I don't like this one personally. Yeah, so we have plenty of space to improve. Yeah, this prefix matching is actually like what we were talking about in this WFST setup. So it means that we are like, as an input to this WFST, we are passing this like first letter or this first two letters. We can, it depends on how many keystrokes the user has made. And after that, we are like doing the things that are described in the WFST. So we are trying to find the paths in this WFST. I'll go back into the slides probably. We stop on this slide. So we are trying to find these steps in this, we are trying to follow these arrows, these arcs in this transducer that would maximize our output. So here, for instance, what would be the maximum? The maximum one would be the one that using data is better and using data are better. So we are trying to find a maximum here that would allow us to maximize to maximize the probability that the user will click on something. Actually, I hope I explained it well. And query autocomplete now. So query autocomplete, it can be like, so we already talked about how can we store the data for query autocomplete. Now the question is like, how can we get those queries? Because like user can type like K, and how do we know that we need to suggest KFC, for instance, coffee, cola, like how do we know what we need to suggest? And the thing is that there are many approaches. Most likely they also depend on the company. They very much depend on the domain that you're working on and on the amount of the data. Also, like I'm seeing from the window now, our Foodpanda courier like driving here while I'm talking about it. So yeah. The main approach that is used like usually for version 1, so this is a very simple baseline, is that we're trying just to calculate the frequency of the words, and this is a very simple thing. So we're just trying to calculate the frequency of different queries that users were historically searching. In the more advanced setup, we're trying to calculate the frequency of different tokens. Then we can advance this logic further. We can try to also introduce the number of orders that users have made for different queries, the number of ATCs, the number also of clicks that were made. And then we also can go even further, and we can develop some weighting, and this weighting can depend on the, for instance, popularity of some meal in some country. Or this weighting can be based on, I don't know, the frequency of some word in catalog data. It can be whatever you can think about in terms of how can we advance it from the point of view of like the data that we have and historical data that we track. Also, another thing that we can do is that we can introduce similarity-based models. And by similarity-based model, I'm saying that a lot of language models, they allow us like to suggest similar like words that to suggest not similar, but rather like different words that, like, for instance, they can start with the same letter that are kind of relevant for the documents that you can have, for instance, inside your data set. So let's say that you have a lot of documents that are talking about, I don't know, physics. It can be some documents about I don't know, Newton's law and Einstein's research and something like that. And you can have the word law that appears often inside these documents, and you can have a word like nuclear and mass and atom and all these other words. And if the user is beginning to write word A, then you can most likely assume that yes, like based on your similarity-based model, most likely you will need to suggest like atom, or I don't know, alpha particles, or maybe something like that. Besides the semantic similarity score of each candidate query, we are also trying to use this frequency-based model. In many cases, by frequency-based model, I'm saying that we can just use like frequency of some token in documents, or frequency of some token in catalog data, or frequency of some token in previously made in the historical data. By historical data, I mean that the user has typed something and then ordered something, and like users, for instance, can be often typing McDonald's and then often ordering something, then like the frequency-based model will rank this token quite high. So here is the example of the score. How can we calculate it based on frequency feature together with similarity feature? And yeah, so you can actually develop what you like. So here we're using alpha as some weighting factor, but you can develop the thing that you like. Yes, and here is the query autocomplete algorithm. It is frequency and semantic similarity based query autocompletion algorithm. I don't like how they call it, like this is a very long word just for query autocomplete. Actually, they're just using this hybrid approach here. So they are like loading, they are firstly training before like they are running this thing, they're training their word-to-vec model, their AOL model. This is like, I think, yeah, AOL model is a word-to-vec model, and Google use model, I think they are using pre-built model, and then they are like introducing model similarity. They're just calling like similarity from word-to-vec, and then they are also like using this frequency score here. And I don't think they show somewhere like, yeah, oh, okay, here like they show how they calculate it. So yeah, frequency score is being calculated here and it's being shown here. And yeah, then they are sorting like these suggestions based on like the weight that they get after we run this formula. And yeah, so give me a second, I'll drink some matcha. Yeah, and talking about like metrics that are related to all of this stuff, because like we can talk about many things. We can talk about expansion, autocomplete, about classification, about a lot of different approaches for query understanding. But the big question is how to evaluate all of this stuff, because it's not trivial. I would say it's even less trivial than building a model, because building a model is in many cases not that complex, but a much more complex thing is to offline evaluate it. We obviously have A/B tests, but A/B test is online evaluation. It requires resources, it requires some time, and also it needs to be agreed with brands in our case. And it's not the simplest process, you know, just to start, because there are different bureaucracy things that happen like during, like before this A/B test is launched. And yeah, it's not very simple. The things that can be calculated and they are relevant to ranking problems and to query understanding problems, and we'll talk about ranking more when we discuss this metrics, is that we can calculate NBCG, we can calculate MAP, MRR, and heat count. These are most popular, I think, metrics. So NBCG is a normalized discounted cumulative gain. It's a popular method to measure the quality of a set of search results. I think like everybody talks about NBCG when we're talking about ranking, measuring the quality of search results and like ranking these search results. So we are trying to assert that very relevant results are more useful than somewhat relevant results, and relevant results are more useful when they appear in the set of results. So here you see the formula for cumulative gain. It is the predecessor of DCG and does not include the position of a result in the consideration of the usable fullness of results set. So in this way, like we are like summing over different relevance position here. And we can decide what this relevant position will be. So 0 can be not relevant and like 1 can be relevant, or in this setup we see that 0 is not relevant, 1 is near relevant, and 2 is relevant. So in this way, it is the sum of the graded relevance values of all results in a search result list. So let's say, let's give an example. So we can have like the user searches for some kind of pizza, let's say, yeah, and we receive like a list of results for this query pizza. And the user clicks on this, the user clicks on the second restaurant and orders from the second restaurant. We also know that the user can order from multiple restaurants. It's not very likely in real life, but sometimes people still do, especially if this is free delivery case. And sometimes we have some kind of campaigns where when we have free delivery from many places. And yeah, let's say that the user can order from multiple restaurants. So we can say that, okay, when the user ordered from a restaurant, then the relevance position, like this term, it will be 1. So we are showing, let's say, first 10 most relevant restaurants to the user after the user typed pizza, and the user ordered from the second restaurant and from the third restaurant. Let's say most of them had free delivery. Then we can say that for this search session, cumulative gain will be 2. And if the user hasn't ordered from any restaurant, then it will be 0. Here we are not taking into account the positions of these restaurants in the list that we are showing to the user. So we're just doing the sum here. Cumulative gain, however, it doesn't reward like these positions that I'm talking about, and we don't reward relevant results that appear high in the results set. And to achieve discounted cumulative gain, we must discount results that appear lower. And the premise of DCG is that highly relevant documents appearing lower in the search result list should be penalized as the graded relevance value is reduced logarithmically. So the idea here is that we would like to rank relevant results as high as possible. Ideally, the user should order from the first restaurant or the second restaurant, but not from the 10th restaurant, because if the user orders from the 10th restaurant, most likely we did something wrong. It can be the case the user can, for instance, love some restaurant that can be ranked as the 10th restaurant, but ideally we should see the case when user searches for something and orders either from the first or the second restaurant. We're not taking into account some other factors here as free delivery or campaigns or some ads or different things. It can happen in the search session. So here it's just the ideal case when the user searches for something and orders from the first restaurant, and DCG purpose is to like make this case really ideal for us. And the final stage of the DCG calculation, it is normalization. If you calculate DCG for different queries, you'll find that some queries are just harder than others and will produce lower DCG scores than easier queries. And we are just trying to solve this problem by scaling the result based on the best results. So if you are saying that you want to see the first result as the best result, and that you are like these relevance positions, if they are 1, like if you assign them to 1, then your IDCG, it should be 1.7, I think. Like this is a constant actually. Like, so this is just a constant that you rate your DCG with. Yeah, and this 1.7 will be if like user orders only from one restaurant and this restaurant is like rated as the first one, and then this is the ideal case for us. Another metric is map. Like usually people are often like relying only on the map, but that's not good, because ideally we should calculate NDCG, map, MRR, hit value, and also precision and recall. But we'll not talk about precision and recall, because I think that's just a too simple topic for this speech. So map is the mean of average precision. Like if we have the average precision for each user, it is trivial just to average it over all users to calculate the map. By computing a precision and recall at every position in the rank sequence of documents. So sequence of documents is the like sequence of like restaurants, let's say for our case. One can plot a precision recall curve, and average precision, it computes the average value of precision over the interval like that we have. It is from 0 to 1. So here is the formula for it. PK denotes precision at some k, and is the number of items in the recommendation list. So it can be, it's fixed number, so it can be 10, it can be 50 in many cases. So usually like we're showing like 10 restaurants, so like 12, 20 restaurants, so it's usually fixed. And relevance is an indicator function which equals 1 if the rank k item is relevant and 0 otherwise. So as I said, like if we are saying, let's say for example, we are saying that restaurant is relevant if the user has made an order for this restaurant, and then we are just averaging stuff here. And map is just essentially the area under the precision recall curve. We can finally calculate this map by like averaging average precision, so it's average over average. But yeah, like it will help just to normalize this value from 0 to 1. Another metric that we can talk about is hit ratio. So I just copy pasted it from one of the articles on Medium because this is a simple metric, and yeah, I don't think we can talk about it for a while. Hit ratio is the fraction of users for which the correct answer is included in the recommendation list of length L. The larger L is, the higher ratio hit ratio becomes, because there is higher chance that the correct answer is included in the recommendation list. So yes, this is just the ratio of users like that were, let's say, that clicked on the restaurant that we like suggested from the list of ranked restaurants. It can be the number of users that have ordered from one of these restaurants, or the number of users that have added to cart from one of these restaurants. And MRR, it's another metric. It's a short for mean reciprocal rank. What it means, it is we are trying to define the sum of relevant score of top L items weighted by reciprocal rank. So it is the mean of all users in the test data set. So to like make it simple, so we have RR, which is this reciprocal rank. It is defined for each user. So we are trying to like divide our relevance, which can be like, let's say 1 for some document over the rank of it. Then we are summing these ranks and dividing by the number of ranks that we have. There are different variations of simplifications for calculation of the reciprocal rank, because obviously you can define your relevance the way you want. And for implicit data set, the relevance score is either 0 or 1, but obviously you can have, let's say, labeled data where you know what that relevance scores can be, not 0 or 1, but something better. For items not what, this is for case for items not what or what, this 0 or 1, but yeah, you can have labeled data and then your relevance will be something better than 0 or 1. And after we have discussed these metrics for like actually measuring how well our model performs, like either query expansion or query classification or query autocomplete model, we can switch into like learning to rank objective and ML ranking related stuff. But before going into that, I just wanted to highlight that we talked about like ranking ranking metrics that are like directly used for evaluation of ranking models. But on the other hand, we still need to remember that this stuff can also be used to evaluate the quality of query expansion, query classification, or autocomplete, or any kind of query understanding model, because these metrics, they are usually kind of like related to business metrics. So business metrics are CVR, ZRR, and yeah, this is the main one. Like it depends on the company what you are evaluating, but usually you are interested in conversions. Usually you are interested in the amount of money user spends, like monthly, let's say. Usually you are interested in not having 0 results rate for search. So NTCG, it's like related NTCG, MRR, MAP, and heat rank. It's usually related to it if we define it correctly. If we define it based on the orders, then yeah, we can like correlate it, and then like you can also measure the quality, the business quality of query expansion or classification or autocomplete for your case, and you can use like all of these metrics not only for ML ranking systems, but it is also useful for query understanding system. So to build a machine learning model for ranking, we need to define like inputs, outputs, and loss functions. So what are our inputs here? It is a query. And for this query, we have n documents, and we want to rank them by relevance. We want to understand that what is the relevance, and we want to rank them from the most relevant to the least relevant. And output for this model is the query document input, where we assume that exists a true relevance score y. Most likely it doesn't exist in real life, because you can never really measure like how relevant is some restaurant for some query, because there are like 100 more restaurants that are also relevant for this query. So you are never like 100% sure that like this is more relevant than this, because yeah, it's very subjective. So outputs of our model is a predicted score, which is a function of our inputs, and inputs are, as we remember, these pairs of queries and documents. So all learning to rank models, they use a base machine learning model. This is like decision tree, neural network, or whatever you can think about, and using it, we're trying to compute this predicted score. And the trickiest part here is the loss function, because these machine learning models for learning to rank, they are different from the usual machine learning models where you are just trying to like make accurate predictions. Here, optimize your precision, recall, F-score. Here, we are trying to make the model learn to rank in the best possible way. And we have three approaches depending on how the loss is computed. So the first one is point-wise methods. It's the one the total loss is computed as the sum of loss terms defined on each document. That's why it is called point-wise. It is defined here as the distance between the predicted score and the ground truth. So we need to have this ground truth here, but yeah, like this is the point of the problem of labeling data. And by doing this, we transform our task into a regression problem where we're trying to like minimize those residuals. We have pairwise methods, and the total loss it is computed as the sum of loss terms defined on each pair of documents D with index I and D with index J. And that's why it's called pairwise. And the objective in which the model is trained is to predict whether one of the labels is bigger than the other labels. So which one of the two documents it is more relevant. And this, then we are converting the problem into binary classification problem, because we are trying to say like to actually solve like this binary classification problem where we have like two labels, 1 and 0. And the last method, it is listwise methods, and where the loss is directly computed on the whole list of documents with corresponding predicted ranks. And this way we are like directly incorporating our rank metric into the loss. So here is just a small diagram of it. And yeah, here is this last listwise method. This is the lost function for it. We'll not go into details of it because I think we're already a bit over the time, and yeah, I'm already not feeling my voice very well. Yeah, but this is like how we can calculate it. So this is also this is not a cross entropy here, because you see here there is no like y log p y given s. So this is more of a marginal conditional probability, if I remember things correctly, where we are using our likelihood of our relevance y. Given S and P, and S is the score and P is the prior probability, if I'm not mistaken, and we are multiplying it by our conditional probability of prior probability given our scores. And obviously, yeah, we are trying to minimize it, so we're using minus here. And this is how actually the majority of learning to rank models works. So they are using these listwise methods because they're the best one for this case. And yeah, for instance, each boost, it has this listwise method for loss measurement. And a lot of neural networks, they also have it. Yes, so I think this is pretty much it from my side. The last thing that I wanted to say is that from the point of view like building of like search system and trying to resolve search problems, I would say that like building a good evaluation matrix is sometimes much more important than actually working on the models, because like building evaluation pipelines, it is sometimes much more trickier than doing all this expansion, classification, learning to rank, and other kind of models that you can think about. And also, yeah, tying up this metrics that you can calculate with business metrics, it's also another trick, because in many cases you should come up with something custom. You should think about how can you correlate like NDCG to zero result, right? Although there is no direct mathematical dependency, but like what user behavior and user scenario you can think about. Yeah, so this is pretty much it, and thank you very much for your attention.